All right, I think we can start. Um, Welcome everyone for this UCAP colloquium today. It's a pleasure to have Jose Luis Bernal. Jose works at the interface between theoretical and observational cosmology. Jose got his PhD from the University of Barcelona, after which he moved as a postdoc to Johns Hopkins University and also to the Max Planck Institute for Astrophysics in Garching, before getting a senior position at the Institute of Physics of Cantabria in Santander in Spain, where he's now. And Jose has special interest in dark matter and the phenomenology of models beyond lambda CDM. And in the past years, he has been working a lot on line intensity mapping, which is a subject of the colloquium of today. So, Jose, the floor is yours.
Okay, thank you very much, Sebastian, for the introduction, and well, also to you and all the organizers for the EuCAPT Colloquia for having me here to talk about my work and research. And as Sebastian mentioned, I'm going to talk about some of my recent work and also work of some of my collaborators related on line intensity mapping. And in particularly, I'm going to be focused on two very recent results, which I think are very important milestones in a couple of collaborations targeting the intensity of specific lines of neutral hydrogen, and it could be the case of the Lyman alpha and the 21 centimeter lines with head and mid class, respectively. But before getting there, let me introduce also what is line intensity mapping. Line intensity mapping is the combination of two main concepts as a way to trace the large scale structure and the universe. On the one hand, we have the fact that we map the intensity, so we use the integrated signal of all the radiation that arrive of the telescope rather than using a given threshold to determine what is a detection or not. We don't try to resolve any source. We use instead all the information coming from all the photons that comes, or for galaxies or diffuse sources such as the intergalactic medium along the line of sight. This could be something, for example, similar as the ways to measure the CMB or the cosmic infrared background, but instead of using continuum emission in order to try to obtain information about the radial distance to us, line intensity mapping targets identifiable spectral lines with a good spectral resolution in order to try to reconstruct that three-dimensional map. Since we are targeting lines that we are that we know that their frequency in the rest frame, comparing with the different frequency channels, we know the redshift that the information comes from, and this way we can build very quickly and cheaper than using galaxy surveys big three-dimensional maps of the large scale structure. And here would be, for example, a show of a spectra of two galaxies. This would be around the millimeter emission, and this is more about the optical and UV. The continuum is something that we will want to remove from the flags that we measure, and the idea is try to, for example, target in this case the C2 line or the C10, the case of the Lyman alpha, bright lines that we can identify well with respect to the continuum.
Jose,
In order to,
Jose,
yes,
sorry to interrupt, but there was a question on the chat, so it's probably better that everyone follows. There was a question which is, sorry, let me just read it. Is it same as
okay.
Galaxy Survey with some low resolution lens, or the mechanism is different from Galaxy Surveys?
So I was going to get there. So
Okay, perfect.
it's true that we don't resolve anything, but we also have the different particularities with respect to a galaxy survey. So in order to make this example, let me use some simulated data. This would be a redshift 5, 1 square degree, and some redshift width of 0.2. And each yellow dot here would be all the halos in this volume. Now, in order to have these resolved detections above a given threshold, we would be dropping many of these, like the vast majority of these sources, especially at such high redshift. This is using just a raw a very rough threshold in the stellar mass, but this would be the idea. We will be only picking the brightest sources that we will have for our galaxy survey, and each of these would be a detected point in our galaxy survey, and then from all that catalog of points, we would reconstruct the large scale structure. Instead, this would be yes. Instead, we want to use all the information that comes from all the population. So, for example, this is results from the time collaboration in which they compare the constraints on the C2 luminosity function from different galaxy surveys, but you don't reach, because it's below the detection limits, the faint end of the luminosity function. And depending on the slope here, you may be missing a lot of the emission, in this case, in C2. This would be, for example, the same plot, but with the constraints on the luminosity function with a time survey in light gray, or a time extended, which would be a similar survey with twice the amount of observing time. And taking this into account, as I was saying, we would be observing a single or targeting specific lines from the spectral energy distribution of each of these galaxies and target those to get the three-dimensional emission and obtain something like this. This is the same volume as it could be observed in CO emission and C+, with the regular resolution, or like the usual resolution of these instruments. This is, if I recall correctly, the resolution that we would expect of an instrument like EuCAPT, and this one as instrument as Concerto. And as you can see, we are basically dropping a very detailed view of the brightest galaxies with very good angular resolution for a lower resolution view of all the sources, because all the intensity that we have here, for example, here we have a very bright point, corresponds to this cluster of galaxies that, of course, will emit in total, the aggregated emission will be brighter than in some regions. But thanks to this, we also can reconstruct structures around here that would be a void, while here we have some intensity fluctuations. So basically, also answering the question that was before, the thumb rule to distinguish between a galaxy survey and an intensity mapping survey is that for cosmology, we would be using a noisy map of all the emitters, galaxies and IgM, versus a detailed map of the brightest emitter. However, with a line intensity mapping survey, we are also subject and sensitive to all the astrophysics that trigger the line that we are interested in, because in a different galaxy with different properties, that line is going to be brighter or fainter, and therefore in this way we can constrain the collective properties of all the population of galaxies, not only the bright end of the luminosity function. So in that case, we get all the aggregate of all emitters and the diffuse emission. Intensity fluctuations are, of course, a tracer of the matter density fluctuation, and in this case, the theory is kind of similar than for galaxy survey, because we will have the matter power spectrum, we will have some galaxy bias, and then we also need to append there the modeling of all the astrophysical processes to model our fluctuations in our intensity. Sorry, I'm getting a bit sick, so I apologize for potential interruptions like this one. So we have already commented some of the main features that make line intensity mapping unique as a tracer of the large scale structure. And the first one of these could be that it captures the faint and diffuse sources that are beyond the reach of galaxy survey. And this also implies that we can reach higher redshifts than with galaxy surveys, because at some point galaxies become too faint and too sparse in order to be able to be useful for cosmology. You either use very narrow galaxy and deep galaxy surveys, something like, for example, James WST, in which you can get a lot of galaxies, but the problem is that like the area is too small to be used for cosmology, or instead you can use this probe, this technique to observe the universe in order to build these big volumes. On top of that, since we don't need resolved sources, we want only like the aggregate contributions with lower angular resolution. We can use low aperture telescopes and scan faster the sky because we don't need those resolved detections. So this makes it cheaper than for a galaxy survey, as it was demonstrated with some estimated calculations in a paper I missed the reference here, a paper by Kiret Katkare and collaborators for this was a white paper for the SNOMAS a few years ago. Of course, with line intensity mapping, we are sensitive to all the new physics that we can probe with the large scale structure. So anything that changes the matter power spectrum, we will be seeing it also in line intensity mapping, but also anything that changes the line intensity function. And that can be anything affecting the astrophysics, although of course the modeling of the astrophysics is more complicated, so it will be more difficult to trace it, or also something that changes the halo mass function. We can also be sensitive to monochromatic signals, such as, for example, some radiative decay of dark matter. We would be seeing it as another emission line in our spectrum. And finally, we also, thanks to this quick mapping of very big volumes, because we would be targeting high redshifts beyond the reach of galaxy surveys, it is expected that we will be also be very sensitive to physics that arise in the ultra large scales, as it can be, for example, some relativistic corrections to the modeling of the large scale structure, or also primordial non-Gaussianities, for instance. I'm going to be focusing mostly on line intensity mapping after recombination. So there's a lot of different phenomenology that goes around for 21 centimeter intensity mapping around the cosmic dawn and the epoch of reionization, both for astrophysics and especially very interesting for dark matter phenomenology. But this is going to be, unfortunately, beyond the scope of this talk. We're going to be focusing at lower redshifts, how is the state of the experimental landscape for intensity mapping in this case, and also what are the prospects for the future. So as I was mentioned, also line intensity mapping allows to fill the gaps in cosmic history that we can't probe directly because it's beyond the reach of galaxy surveys. Right now we have direct probes of how is the universe at the large scattering surface from the CMB, at lower redshift from galaxy surveys, and then it's true that we have some integrated contributions from, for example, CMB lensing, but CMB lensing still peaks around redshift 2. Intensity mapping aims to fill this gap and provide direct access to higher redshifts, even beyond reionization and the cosmic dawn. Here, in the plot on the figure on the right, I have a summary, which is always outdated because the landscape of experiments in line intensity mapping is very active. But here I'm showing some of the experiments as function of the redshift that they probe, and the area on the sky that they cover. Different colors correspond to different spectral lines that are targeted, and then solid lines are experiments that are already running, and those lines are experiments that are funded but haven't been started observing yet. And as you can see, it's very easy to see already some kind of cluster here of 21 centimeters at larger areas on the sky. And this is mainly because 21 centimeter has been historically more studied both theoretically and also experimentally. But there have been an increasing interest in other lines, such as, for example, millimeter and submillimeter lines, like a CO and the fine structure line of C+, and also optical and ultraviolet lines as Lyman alpha and H alphas, that in this case I would be probed by spherics and hetex. Most of these experiments are still in the Pathfinder stage, and that's why they are focusing on such a small areas on the sky, but they are already increasing quite good thanks to the good results that they are finding. As you can see, there are already a couple of things that we can see from the fact that we are observing with intensity mapping so many different lines, and the fact that this is that intensity mapping is intrinsically multi-tracer. You don't need to go to, for example, cross-correlated with galaxy surveys or CMB lensing. You can use always different lines to do multi-tracer cosmology. And also that could allow you to probe all kind of different astrophysics because each line is sensitive to different processes and can be a tracer of different properties of its galaxy. And specifically for the point that we are right now, the fact that we can cover so many, a range of frequencies that is so wide, it's very interesting because this means that both theoretically and instrumentally, each of these observations is going to be subject to very different systematic errors. Sorry, and this means that also we can do cross checks between different observations to be more robust on our measurements.
Jose, let me take
Okay.
the opportunity of that of your small break. There were also some questions on the chat. Maybe we can also, I mean, I'll take a few, but maybe we can postpone questions for the end. But
Okay.
let me just take this one. There were basically two questions. One some time ago, which is why it hasn't been done before. Basically, it's written if it can be done using low resolution lens, then I would expect people should start it earlier than galaxy survey. So, what were the difficulties in doing this before? And a second question more related to what we see just right now. What are these vertical small cuts in the horizontal lines? Like
Uh,
being
you,
phased
you,
by
you-
some critical cuts.
okay. So I'm going to answer second, like first the second question. So there are some cuts here that are basically the fact that in some of these experiments target more than one line because these are going to be line interlopers. This can be contaminants, but also is another signal. This is basically different emission lines that redshift into the same observed line because they are at different redshifts. I'm going to cover them later as one of the main problem. And for example, this could be the case of spherics that covers a wide frequency range and can observe both Lyman alpha and H alpha, but also has some contamination from the oxygen lines. Or the case of headlegs that has also O2 contamination at low redshift. And then to the first question is going to be a big chunk of the talk. The main problem of this, I'm focusing first on the good things, but intensity mapping also comes with a lot of challenges. That is mostly the fact that since we are observing all the flags, our experiments are going to be noisy because they're going to have the instrumental noise included in the readout of the flags that they get. But more importantly, we're also going to get all the contributions from foregrounds that makes these measurements more complicated with respect to galaxy survey. However, we all think, people working on intensity mapping, that the potential is worth the effort on overcoming these challenges. I'm going to be focusing on these things later. But before continuing with the talk, I wanted also to highlight that I've mentioned that most of these experiments are in the Pathfinder stage, but still there have been already some detection of this line, most of them in cross correlation with galaxy surveys, some of them also in autocorrelation, as it would be the case of COPs at very small scales. Then we have also MIME, these are CO lines that have been detected. Then using observations of Planck and other infrared and microwave experiments, as for example Herschel and IRAS, have been some detections on the intensity of these lines using, as I said, quasars and galaxies. Again, C plus at high frequency for Planck, and at lower frequency would be the CO line 32. There have been some detection of 21 centimeter with the Green Band telescope, and very recently, Jiquan Qian had a very interesting paper on the archive using a galaxy survey and the clustering-based redshift to study all the continuum and emission lines that you can detect from Planck, Herschel, and IRAS. However, I'm highlighting here in the plot another three experiments that have had detections. Hedex and Mirklas, I'm going to go more in detail later. And Time had is this interferometer that observes very big areas on the sky, as you can see on this plot, and they have had some detections of 21 centimeter at a redshift around 1.5 in cross correlation with galaxies, and very recently, some months ago, they put on the archive a detection at the smaller scales in autocorrelation, which was also something that was done using the MEERKAT telescope a couple of years before, even at smaller scales, using also interferometry. Okay. Let me focus also first on how we get the information returned from these intensity maps. We are cosmologists. We work with the power spectrum. That's the first thing that we try to measure all the time, whether when we have a map. And in the case of the intensity mapping power spectrum, at linear order being as simple as possible, we can distinguish between some clustering and shot noise component, where the clustering is proportional to the matter power spectrum, as usual, and then multiplied by the mean, the square of the mean of the temperature times the bias, the temperature of the line. While on the second case, on the shot noise, if it's Poissonian, and this is a big if, we can discuss about that later, because we need to be very careful about how we interpret the intensity mapping power spectrum at very small scales in this regime. It could be sensitive to the second moment of the line luminosity function. However, intensity maps are very non-Gaussian, because on top of all the non-Gaussianities that we have due to the gravitational collapse that are also there for galaxy number counts, we have all that added to the complexity of the emission line. Each of these galaxies is going to be weighted by the intensity of the line in the galaxy itself. So we would be leaving a lot of information beyond the power spectrum. As for instance, if we want to focus on astrophysics, here we're getting only the first and second moment of the luminosity function. So if we have access to other information than the power spectrum, we would be accessing more information about the astrophysics, and also we would be able to break some degeneracies between the astrophysics and the biases and cosmology. There are many options that you can use here. You can use, for example, third, fourth order, for 4-point functions, but I personally have worked on what we call the Boxer intensity distribution, that is 1-point distribution of intensities, and this is a proxy of the full luminosity function, because the 1-point probability distribution function of a given of measuring a given temperature on a voxel or on a given volume is the sum of the conditional probabilities of finding n emitters in that volume, and the combined probability that all those emitters aggregate to a given temperature T. And this factor here is just a convolution of n times the luminosity functions. And this is why the Boxer intensity distribution is too powerful to constrain the luminosity function of the line of interest. Again, a rule of thumb, the power spectrum would be the best for cosmology, but it depends on integrals of the luminosity function, while the Boxer intensity distribution would be the best to constrain astrophysics, but it depends on integrals of clustering. Therefore, here we can take the best of both worlds and combine them. If we do this with an appropriate covariance that was derived in a paper that I did with Gabriela Satopolito back in 2022, this can, as we expected, improve quite a lot the constraints. These are some results from the COMAP collaboration in a simulation-based analysis, in which they showed that combining the power spectrum and the Boxer intensity distribution, the sensitivity to the luminosity function increased a lot. This is the luminosity function measured from only the power spectrum. This is the same from only the VAD, and this is the combination. And here you can see the relative errors are much better when things are combined. In some cases, even improving over half or one order of magnitude. Another thing is that, as I was advertising before, in this paper led by Vivian Sabla a couple of years ago, we demonstrated that by combining these two summary statistics, we can break the degeneracies between astrophysics and cosmology, and this would boost the sensitivity to beyond lambda cold dark matter models. In that paper, we explored ultralight actions and primordial non-Gaussianities, but this would be general for any model beyond lambda cold dark matter. But in any case, you always need to account for resolution effects, observational effects, and so on. And this was discussed in this paper that I wrote in 2023. Okay, so I have been talking about all the good things that can come with intensity mapping and all the potential that it has. But there were already some questions before about why this hadn't happened before. And this is because real life always comes with some problems. You can't have it all. And this main problem are the foregrounds, but we are progressing very fast in the observational side to deal with this. Okay, so let me come back to this figure that I showed before. Here, we would be having the target line that we would observe, but intensity mapping gets all the emission along the line of sight as function of frequency. So we are going to get also all the contributions that we are not interested in. And in this case, this includes the galactic foregrounds, all the extragalactic continuum emission that is along the line of sight, and also these line interlopers that are, as I said before, emission lines that are at different frequencies than the target line, coming from different cosmic volumes, but that they received onto the same observed frequency. This would be the case of the galactic foregrounds. This is the regime in which this is most complicated. It's on the radio surveys for 21 centimeters. And this is because just the mere ratio between the amplitude of the galactic synchrotron and the signal that we are interested in this case would be the red line and the blue line, is just huge. So if we want to clean the foregrounds and model them to remove them from our maps, we need to do this in a very, very precise way, because we will need, in this case, for example, we will be removing something that is 10 to the 5 times larger than the signal of interest. So we will have to know our synchrotron with good spectral resolution with a 10 to the 5 precision. And that's something that we don't have yet. And this is why we need blind methods, usually principal component analysis or similar, in order to clean our observations. Of course, we don't only have the synchrotron. There are more contributions from, for example, point sources or free, or things that complicate quite a lot this separation. We have instrumental noise that, even if it's quite low, it complicates a lot the cleaning, because they mix the components. And the main problem, at least in the case of Mir class, but I think that this is something general to any 21 centimeter experiment, polarization leakage, that again mix the components. So when we are going to do this PCA and remove the modes with highest variance, that we assume that are the residuals, we are going to incur in some signal loss. And this is basically can be corrected with some transfer function. What we are doing at the end of the day, in order to improve the separation between these components, is use the fact that both spectrally, as you can see here, the foregrounds are very smooth and our signal is kind of noisy. It has a lot of structure at small scales in frequency. But also the angular features of the foregrounds and the signal of interest is very different. And this is why we can also exploit angular information in order to do this component separation better. I have already introduced a couple of times the line interlopers. This is just an example of what they are. Imagine that we would be focusing at C plus here. At Redshift 2 is fine because it's much brighter than any other line at this frequency. But if we go to higher redshift, for example, redshift 5, 6, around this here, we need to be careful and clean very well all the CO ladder that is as bright or brighter than our line of interest because they come from lower redshifts too. This is another example of how it looks and how it changed our measured power spectrum multiples. This would be the monopole and the quadrupole, and the BID. And this is a simulated example of C plus only and also including all the CO emissions at different redshift. And you can see that things change quite a lot. There are different ways to clean this, either masking or we can model them using the projection effects. The only problem with model them is that sure you're going to have information, but usually the lower redshift interlopers are brighter than the signal of interest, so you will have to change the goal of your analysis. There are also spectral templates and multi-line intensity mapping ways doing cross frequency between the channels, cross frequency correlations, and also nulling techniques using correlations with lower redshift tracers of the large scale structure that may be correlated with the foreground interlopers. Interestingly though, if we have some exotic particle, like for example axions, that decay into 2 photons, this would be another line interloper that we wouldn't be expecting, and we can use the same techniques that we have in order to clean these interlopers to look for this exotic signal. This is something that I explored back in 2021 in this paper. We were discussing how spheres and headdeck should have the potential. Of course, this is in very idealized situation in which we don't have foregrounds and so on, but to improve the sensitivity to the action around the multi-electron volt mass. And something similar would happen for some millimeter probes as COMAP, CCAT prime, and at last for the neutrino decays. In this case would be neutrinos with a mixing that would be beyond the standard model, and basically we'll be measuring the effective transition moment of this transition between the flavors of the neutrinos, and we would be getting constraints that could be much better than current constraints from the CMB and on the order of magnitude from experiments that like the Borexino or indirect probes from astrophysics as the tip of the red giant branch. Okay, now I focus on the worst part, which are the interlopers. Now let me focus on the interesting part, that is that we are actually dealing with this problem that many people thought that it would be too challenging. But not only that we are getting very interesting results and we are achieving very important milestones for intensity mapping as a observational technique. So, Sebastian, I don't know if there were any other questions. Maybe it's a good moment to ask them, or I can continue.
Let me check. There were some questions, but I had in mind that maybe they were a long time ago, and somehow you already answered them, I think. Maybe, well, maybe people will ask the question. There was, why is line intensity mapping statistically more powerful than galaxy surveys at high redshift, and why are intensity maps highly non-Gaussian? But I think the last question was asked at a point where you have not explained. But now I think it's clear, but people can explain more.
So basically, to answer quickly, the first one is that the shot noise, or the noise, the base noise that you have with galaxy surveys goes as 1 over the number density of galaxies. And at higher redshift, you are going to have less galaxies intrinsically, and also galaxies that are going to be fainter for us. So detecting them are going to be harder, and basically you're going to be limited by that shot noise for cosmology, while in the case of intensity mapping, you're going to have some other problems as the foregrounds, but you will be able to probe better that regime if you get to measure it. Okay, so in terms of the experiments that we have that I'm going to focus, I'm going to focus on two of the collaborations that I'm involved in. One of them is MIRCLASS that measures the 21 centimeter with the MIRCAT telescope, and the other one is going to be HEADEX. So I'm going to be focusing first in MIRCLASS and then in HEADEX. As I mentioned, MIRCLASS is a collaboration that uses time of the MIRCAT telescope, aiming for a large scale cosmological 21 centimeter surveys using a single disk approach. So this is not interferometry. This uses the antenna only in autocorrelation mode. And we are prioritizing patches with overlapping galaxy surveys just for cross correlation and verify our results. Again, MIRCLASS is a pathfinder for the SKO. So we are just showing and developing the technique and demonstrating that this is a feasible technique. The first result that we had were in the L band, that this is for redshifts below 0.50A, although at redshift below, in this band, we are very limited in redshift due to the radio frequency interference. And we have around 100 hours observed, and I'm going to show results for this band. But I also want to highlight that we are currently already undergoing the UHF large-scale survey, and this is basically what is shown here, in which in the UHF band that goes from redshift zero point 0.4 to 1.45, we are aiming to have a 10,000 square degrees 21 centimeter survey. The final footprint is expected to be something around this dashed red line. This plot is already 1 year or so old. We have more patches of the sky observed. And at the end of the year, we will have observed for 1,400 hours and observed for 5,600 square degrees of the year. The whole project that is approved, and I quote it in a way because we need to renew it every year, aims for a total of 2,500 hours. So as you can see, we're already, at the end of this year, we have already passed the equator of this project that is expected to finish observing in 2028. So back in 2022, doing the first analysis of the L band, we obtained the first result in cross correlation of 21 centimeter with the Wigglesy bands. And I mentioned before that we had to remove probably lots of modes due to how big the foregrounds were and how mixed signal and contaminants might be. And this is an example. We had to remove 30 modes, and that incurred in a lot of signal loss. And this would be how the transfer function looked as function of scale for the different number of modes that we would be recovering. So we had to correct for losing 30 modes in our PCA, and this is why we were missing so much information. In any case, even after accounting for that in our covariance, we found in this paper led by Steve Cunnington and Jichin Lee, we had only with 10 hours of observation already a 7.7 sigma detection of the power spectrum. So that was already very reassuring that things were going along the good way. And this was for the first L-band method. However, we thought that we could clean better the foregrounds rather than with a naive PCA. And what we do is what I mentioned before, of using also the angular information or the spatial information due to the foregrounds having a very different spatial or angular features than our signals. And this is basically what is called a multi-scale, or what we call a multi-scale PCA, that is based on basically separate between small and large scales, and then run a different PCA for each of those maps, and afterwards combine them after removing the number of modes of each map that we need in order to clean the maps. On top of that, we were a bit smarter on how to deal with all of this because PCA deals very poorly with outliers. So what we did was focus on a smaller but more uniform footprint. So rather than using all the painted region here, we were using only the cyan um, region that assured us that things were going to be very uniform in the amount of the noise or observing conditions. And by doing this, we managed to, with the same observed data, go from 30 modes that we had to remove only 4 large scale modes and 8 small scale modes. And by doing this, we were, without any transfer function, recovering a very similar power spectrum, very consistent, and even with higher amplitude parameter significance. Here, I'm not quoting the total signal to noise ratio of the measurement of the power spectrum, but the significance of an amplitude of our feed for the power spectrum different than 0. And we were having a better parameter significance, even without the transfer function. Okay, let me go quicker for the something that is very nice. I'm going to uh, pass over the cross correlation in the L-band deep survey that we had that were consistent with previous results, also in stacking. But I'm going to discuss of something that is currently underway, that this has been submitted to the journal. This is a collaboration-wide effort led by the PhD candidate Matilde Barbier-Squarotti, and is actually aiming for the first detection of 21 centimeter on cosmological scales, on scales that are large enough to be dominated by the clustering component of the power spectrum. Now, this is more complicated because when we cross-correlate intensity mapping and galaxies, the foregrounds are not in the measurement, are only on the covariance. But when we do the autocorrelation, we would be also including systematics and foregrounds on our measurement of the power spectrum. In order to deal with some of this, we did some internal splitting. So we split our data on all the antennas that we were observing and different times, and did correlations of maps that have been observed between different antennas and at different times. And this allows us that we have no noise in our signal and also in our measurement of the power spectrum. And also we also remove any uncorrelated systematics that are this or time-like. So this allowed us to better significance and a more robust measurement. We applied the multi-scale PCA, and in this case, we had to remove around 10 modes for each of the sets and for both small and large scales. And we developed a formalism in which now our data vector is this combination of two power spectra of the two supercross combination of the internal splitting of our data that we were doing. Rather than try to correct for the signal loss with the transfer function, since having a model for the transfer function is more complicated and we are still developing it for the autocorrelation and the internal splitting, we use a power loss suppression for each of the power spectra that we measure. So we end up having three parameters, which could be the amplitude of our intensity mapping power spectrum, which would be the same for the two power spectra, and the two spectral indices modeling this suppression due to the signal loss. We estimated our covariance with the jackknife, and it was this is still preliminary. We have been working a lot on all the the control tests and null tests in order to cross-check that this is actually a cosmological measurement, but we were very optimistic with the result because we have found something that is robust to all our tests and is a 7.3 signal-to-noise ratio in the measurement of the power spectrum in autocorrelation at cosmological scales, which this would be the first time that this has been done. Now, the covariance that we estimate is only for the volume that we observe. So if we want to do parameter inference, for example, of the total of the amount of hydrogen that we have in the universe rather than the amount of hydrogen that we have in the volume that we observe, we need to include the supersample covariance, that this is something that is currently under development by Sefa Pamuk, who is doing the PhD with me. And as you can see, our measurement for the amplitude of for the abundance of hydrogen times the bias is consistent with our previous measurement in cross correlation with galaxy surveys. However, the error bars are much larger due to the degeneracies with the signal loss. If we were to ignore the signal loss, we would be getting a much better detection significance for this amplitude, for this mean abundance of hydrogen in the universe, also still consistent with the previous measurement in cross correlation with galaxy surveys. So this is all very reassuring all the time. Okay, now let me go to headaches. So changing a bit gears, changing a lot the frequency that we are focusing in. This is still neutral hydrogen, but rather than observing it with radio telescopes, we are using optical telescopes to observe it. And the optical telescope that I'm going to be talking about is the Hobby-Everly telescope from the University of Texas, and the HEDEX experiment, that is a blind IFU Lyman alpha emitter survey over 450 square degrees on the sky at redshift between 2 and 4. So it could be these red bands here, this one and this one here. And this corresponds, since it has a high redshift, to 11 gigaparsec cube volume. The main objective of HEDEX is to measure the BAO and redshift space distortions at this high redshift in order to measure the evolution of how the universe was expanding and put constraints on dark energy. But the problem is that if we want to use only, not the problem, but something that is still there, is that most of these fibers in the IFU instrument are not going to detect any galaxies. So that could be all information that could be thrown away. For example, this is how, in a simulation done by Chris Birol, the Virus instrument, that is the instrument in the HED telescope for the HEDEX experiment, and each of these squares are filled with optical fibers. So if you have this point of view, you could be detecting different galaxies here, but this could be all your signal. So you would be getting only few galaxies of this, but throwing away all the fibers that have some signal, but it's just not above the detection threshold that we have. So what we wanted to do with the intensity mapping survey, that it has been, again, a collaboration-wide effort, but in this case had been led by Maya Luhani-Meyer, which was at this time a PhD candidate in the Max Planck Institute for Astrophysics, but has recently defended successfully her thesis. What we wanted to do was use all that data. So basically, we were doing an intensity map, always tracking the noise levels, because we want to account for the fact of the galaxies that we detect. So we are going to mask the detections or the fibers that have detections, and what we want to do is cross-correlate our intensity map with the galaxy catalog that has been detected by the same instrument. Now, cleaning the sky on the optical is very complicated. This is again underway work, but this is why in this work we have been focusing on scales that are within a given field of view, because we would be losing coherence between different pointings. So, but we're improving our sky model in order to be able to access larger scales. And as I was saying, basically what we want is cross-correlate detections and intensity maps without detections. And we're going to do this in 3 redshift bins over the 3 different fields that are observed by HEDEX. This could be the fall, the spring, so this would be basically these 2 fields. And then in the north ecliptic plane, there's a small field of 10 square degrees that we could still use. So at the end of the day, we're going to have 9 measurements, 3 redshift bins for 3 different fields. We are going to do a different PCA cleaning for each of these measurements. And we are going to be removing modes until we get a consistent amplitude in the 3 fields, because again, the Lyman alpha intensity mapping has to be the same for all of them, the power spectrum amplitude, and in this case, the signal loss is going to be forward modeled with a log normal mog signal injection. This is a summary of the results that we get. This would be the combined measurement of those 9 measurements, and this is something that was very cool with we saw it because combined, this is a 15 sigma signal to noise ratio, which, as far as I know, is the highest significance line intensity mapping measurement to date. This is, of course, in cross correlation with a galaxy survey, but still, it's very cool. This is already a very high significance measurement, and we can already use it to inform astrophysical models. Because, for example, from the amplitude of this power spectra, we can measure the bias of these emitters times their mean intensity, and comparing with previous measurement of or attempts to do a line intensity mapping with Lyman alpha. These are efforts using the BOSS survey, cross-correlating quasars with the Lyman alpha emission that was on the outskirts of the fiber, but these were very complicated measurements, both with quasars and the Lyman alpha forest, because in the way BOSS worked, the instrumental systematics were very problematic in this case. They did a lot of work and a very good work, but we believe that our results with the virus instrument in HEDEX are more robust just because we don't have the plates with the holes in fibers that may induce a lot of reflections in the non-detection. And also the fact that HEDEX is a blind survey, so there's no targeting involved, and we're getting a very complete signal of all the emission that is coming from the volume that we probe. And with this, we also can infer the mean luminosity density of the undetected sources if we compare it with the sources that we can detect. So this is basically a comparison with a simulation of the Chris Birol and Nelson in 2023, which is at redshift 2, and this would be the total signal, the signal from the circumgalactic medium, and the signal from the intergalactic medium. Finally, the faint galaxies that are not detected could be the faintest contribution, and this could be our results, including or not marginalization over different uncertainties, especially the bias of the emitters that we have into account. And we can compare this with the results extrapolated from luminosity functions that, again, they provide a very good measurement of the bright end of the luminosity function, but then they extrapolate that to lower redshift. So you really don't know if you are here or here or here because it depends on that slope that we don't know how it is. This is already very cool because with a, not preliminary because the paper is accepted, but a first attempt at measuring the Lyman alpha power spectrum in cross-correlation with galaxies with HEDEX, we can already observe and inform astrophysical theoretical models and simulations thanks to these measurements of all the luminosity in all the budget in Lyman alpha photons that can be detected, that is there from sources that are beyond the detection limit of HEDEX. So now we know and we have budgeted all the Lyman alpha emission in the universe in this redshift range. So with this, I'm not sure how long did I take for this because I can't see any time. I can talk for longer and more things related with intensity mapping if people are interested and I'm too soon, but let me go with the conclusions for the topics that I've discussed. I hope that I have convinced you that line intensity mapping has the raw potential to become a pillar for cosmology and astrophysics, thanks to its unparalleled access to the faint and the high redshift universe that make it very complementary with other probes, such as, for example, galaxy surveys. And this is because it can capture faint and diffuse sources and access beyond the reach of these galaxy surveys, since it does not require these resolved detections, and also allows for a quick map of the large three-dimensional volumes. However, we need to go beyond the power spectrum once the maps are precise and clean enough, because the maps are going to be very non-Gaussian, and otherwise we will be throwing away a lot of information. And if we combine, for example, the power spectrum and the one-point functions, we can break the analysis between astrophysics and cosmology and obtain much better constraints. However, we have to also keep our feet on the ground and keep in mind that foregrounds are a very important challenge that we are working to deal with them. I think that we are progressing quite fast because, for example, for interlopers, there's a lot of complementary strategies that can be combined, and especially for Continuum, there is the multi-scale PCA is working quite well, and we are working on different ways to add even more angular and frequency information. We have very important milestones recently. I have discussed the highest signal to noise ratio for light intensity mapping with headdex, the first measurement in autocorrelation at cosmological scales, but let me also discuss how these things are going to evolve in the future. So time, I mentioned before, the small scale detection in autocorrelation is very high significant. This is 12.5 sigma. It's an incredible result. And they are going to upgrade to cord that they're going to use these antennas rather than the interferometer. So they expect that the beam is going to be much better than in the case of chime, because the beam of a dish is much better controlled than the beam of the interferometer in the cylinder. And they are going to attempt a VAO measurement with cord. And in mid-class, we have a very clear roadmap. We are going to the wide survey, aiming for also for a VAO detection. And in headdex, we are already ready to inform theoretical models, but we are expecting to improve our analysis of the data that we already have. We are going to come expecting to obtain more data, but especially we are working on a better pipeline, especially for the cleaning of the sky, which is right now one of the main limits for our pipeline. So hopefully we can observe the quadrupole or even measure the VAO, even if in cross correlation with galaxy surveys. So also there are more surveys that are going to be wider. For example, SKO. There are more surveys that are coming online every day. So I think that there's going to be a lot of opportunities for multi-tracer. And I have a lot of hope on the next generation of line intensity mapping experiments. And I hope that I have convinced you all about this.
Thank you very much, Jose, from my side and on behalf of everyone. There were actually many questions in the chat. Some of them were partially answered by Eiichiro Komatsu, but who had to leave. So I suggest that maybe the first people, Wajdan, Jamal, and Durba, who had many questions, maybe to ask them live, or if they cannot, I will read their questions, but that may be simpler. Wajdan, Jamal, or Durba, do you want to ask your question yourself, or should I read them? Okay, please read them. Okay, so let me. You can also see them in the chat and ask them in the right order that you prefer. Let me.
Yeah,
The first one that
let me
was
see.
not, but I can. You can have a look, but I can also
Okay. Yeah,
read
that'd be better.
them.
Thank you.
Right. So the first one, so some of them has been partially answered, but is there a theoretical limit where blind foreground cleaning inevitably removes parts of the cosmological HI signal? That's
Yes, and this is something that we've already seen. For example, here, this is the measured. So basically, this is what we see of the signal that has been lost. So in this first measurement that we did with Mirclas in 2023, the component separation was not advanced enough that even with blind, that like so we do blind because we don't trust the parameterized models have enough accuracy for this goal. And in this case, we already saw that there was a lot of signal lost in this case. And I don't have the plot here, but in the paper of headdex, we also have some signal loss as we increase the modes that we remove. So the only thing that we can do for that is improve the component separation techniques, including more and more features to be able to separate better contaminants and signal, because at the end of the day these blind methods, only the separation that they do is statistical. They go for statistically independent components, but we want physically independent components. So that's why we need to improve these methodologies in order to minimize the signal loss.
Hello,
Thank
am
you.
I audible?
Yes,
Hello?
we can hear you.
Yes.
Okay. So I have a question. The formula you showed there, that power spectrum, that matter power spectrum is linear matter power spectrum, right? In the formula
You
of linear power spectrum.
mean here?
Yes, that matter power spectrum is linear matter power spectrum, right?
Yeah, this is like a very simple case in which everything is linear. This is just as a illustration mostly.
Okay, actually the lim code which is there in GitHub, that there it is non-linear. So I have become very confused regarding that whether this same formula will be useful for non-linear also or not. Maybe we can have something else if we use non-linear metaperspective.
So it depends on how you expand your results, but if you go to not like this can be perfectly the nonlinear matter power spectrum too, and then keep everything linear. You want to be as consistent as possible on your nonlinear expansion, but the first step is using nonlinear matter power spectrum and just multiply by some amplitude with the mean temperature and the bias.
Okay. And do we have any VID data for any limb experiment?
Any what data? Sorry, that it cut there.
VID data, voxel intensity distribution data, as we have some power spectrum data.
Uh, So not really, because the main problem that the voxel intensity distribution has is that it's much more prone to be affected by systematics. So the cleaning that is needed to have a robust measurement of the BID is significantly larger. It's like the cleaning must be much better to obtain a clean measurement of the BID than of the power spectrum. So far there has not been any measurements of the one point statistic as far as I know.
Okay, thanks.
Thanks very much. So there's been confirmation that it's better if I read because there's a problem with Mike. There was one question some time ago. I don't remember exactly for which plot. I'm sorry, but let me read it. The question was: Is signal to noise ratio equals 7.3? Does it remain stable under different covariance estimation methods?
So I guess it's here. Yes.
Yeah.
So the main problem here to estimate the covariance is that we need to do it from the data in order to account properly for everything that goes into the measurement that is very hard for us to model, especially the foregrounds are potentially foreground residuals or how the signal is lost and so on. So that's why estimating the covariance from simulations or analytically is extremely complicated and not very reliable in this case. You can do something similar, for example, as we did with headdex, that was basically inject many different kind of mock signal, but basically there is more limited also by the instrumental noise and the residual foregrounds, if I recall correctly. And at the end of the day, it's also the fact that you are using the same foregrounds all the time because you are injecting your signal in the measurement and then doing the PCA from there. It's a pity that 8.0 has left because maybe I'm doing something that is not 100% sure, but it's very well described on the paper. In this case, for mid class, we had to do jackknife covariance from the data in order to be very reliable. The results are roughly consistent with a Gaussian covariance, for example, with an estimate of the residual noise in the measurement. But we are also always going to trust more over jackknife covariance that also includes a better account for mode coupling due to all the PCA and all the treatment that we do in the data in order to clean it and to be ready for a measurement of the power spectrum.
Thanks very much, Jose. I think there was only one question that I was
Sorry. Can I
unanswered.
ask one more thing? I couldn't
Yes,
hear the
sure.
thing clearly at that time. So the thing is that that means you are saying that I can use nonlinear matter power spectrum in the limb power spectrum formula. Means actually I saw in the GitHub code that they are inputting the matter power spectrum as nonlinear matter power spectrum. So can I do that with the same formula?
Yes, so at the end of the day, it depends on what you want to assume, but roughly the same formula, whether the matter power spectrum is linear or non-linear, is going to depend on what you want to do. And depending on whether you continue expanding your theory on perturbation theory or whether you use something like halo fit, you need to be careful and assume different things. But if, for example, you want to use the halo fit nonlinear power spectrum and the formula that was there, that is like a rough, simple linear case, I think it should be okay.
Okay. Thanks.
I have a question. Is I'm audible?
Yes, you are.
Yes, you are. We can hear you.
My one and last question is that how do we know that the information LIMX extracts is generally new or not a blurred version of what Galaxy survey already measured?
Okay, so on this regime, that so far we are overlapping with galaxies because again we are in a Pathfinder stage. It's not going to be 100% new, but it's going to be a different tracer of the large scale structure. And always that the bias is different enough. This is basically that it traces different emitters on different kind of halos that the galaxy surveys are tracing or that they are covering. Is going to have complementary information to the galaxy surveys and they can be combined. This is, for example, what you will have from a multi-tracer analysis. And in that case, it has been shown that you can beat down cosmic variance and reduce the the errors that you have or the covariance, basically because you have two different ways to probe the same large scale structure. But in this case, in any ways, with this, what we want to do is to demonstrate that this technology works, to take it to the next level and push it to higher redshifts, where galaxy surveys are more limited. This is for cosmology. On the case of headdecks, for example, or in this case for H1, if you want for 21 centimeter, if you want to study the astrophysics of it, for example, if you want to budget all the meters or all the emission that you have in the universe in Lyman alpha, intensity mapping is the only way to go because otherwise you are going to ignore all the meters and all the populations that are below your detection thresholds. And you have to be very careful about that because extrapolations may or may not work.
Okay, I understand. Thanks for your answer.
Okay, welcome.
Is there any other question live? I think we've answered all questions that were in the chat. And well, the time is appropriate. So I suggest if there's no other question, that we all thank Jose for the very nice colloquium.
Okay, thank you very much, everyone.